Okay, so now we're going to go over the results from the predicted structures from the different um, features that we used from Quark, Raptor, Swiss Model, and Scratch. And so here is the results from Raptor. You'll get an email saying when your job is finished, and you can click the link that they provide to the results page. And they give you some additional information here. Go ahead and you can download the PDB file that they gave you in the email. And with Quark, they should send you an email with a link to the results, and they should provide a PDB file as well. Go ahead and download that too. And we're going to be using Pymol. You can use Chimera too, and we're going to be visualizing the protein structures and looking at the different structures that are resulting from the different methods that we use, like homology modeling, protein threading, and so forth, and de novo. So we're going to go ahead and look at the structures. So we can open up Pymol or Chimera. I already have a tutorial with Chimera, so you can use Chimera if you have any trouble with Pymol. I just prefer Pymol because I've been using it more. Okay, so first I'm going to fetch the PDB file, or the PDB file for drosomycin. So this file right here, if you go to PDB and you type in 1MYN, you'll get this is the protein structure that's been experimentally predicted or experimentally determined. Okay, and this protein structure is it's just the actual sequence here. It's not including the propeptide or the signal peptide. It's only position 27 through 70. In our submissions, we included the entire protein sequence, which is 70 amino acids long. So we can see what the structure looks like. Well, at least we can get a prediction of what the structure looks like, including the signal peptide and propeptide. But I'm going to first fetch the PDB file from the protein data bank. So this is the NMR structure, and then we can load. I'm already in the directory of where I have the predicted structure files here from Quark, Raptor, Scratch, and then the PDB, and then the Swiss model. So I'm going to load these in. So I'm going to load drosomycin. Going to load Quark, load Raptor. I'm going to load Scratch. So these are the structures right here. So let's look at Raptor. Let's look at Raptor and the NMR structure. So here, Raptor is in yellow, and then green is the NMR structure of drosomycin. So just remember, we included in the structure predictions all 70 amino acids. I'll show the sequence here. Position 27 through 70. That section is drosomycin. The NMR structure is only drosomycin. Rest up to here, from 1 to 26, is going to be the signal peptide and propeptide. Here I'm going to align. Raptor with 1MYN. And as you see, the root mean square deviation is really low. This is the root mean square deviation is the average distance between each of the atoms being aligned, or the residues being aligned. Right, so this is real similar. We can look at other structures here. Let's look at what Quark predicted. Quark is Raptor predicted with protein threading, and with drosomycin, or with Quark, This was done with ab initio, so from the structure, from the protein sequence itself. So we can align these. Align quark with 1n, yn. And here we get our alignment here. We can reset this, get our alignment here, and you can see where there is some similarity, but the value isn't as high. The root mean squared deviation isn't as low as it was for Raptor. So we have an average of 2.785 angstroms. That's the average distance between each residue. Let's look at Scratch now. So Scratch, and so we can align these two. Scratch and 1n. We have a really large root mean square deviation value. So it means most of them are pretty far apart on average, the distances between each residue. Just remember, with the root mean square deviation, we want a lower value. In this case, we want a lower value. So next we just have, let's compare the homology model with the actual NMR structure, which they should be really similar to each other already, because the homology model that we built, was based off of josomycin itself. So they should be really similar, if not the same. So align joso and 1 yn. Here we have, so really low deviation. And if I remember correctly, Raptor had an even lower root mean square deviation. Okay, so this is homology modeling, but what if we use the homology model, just say we didn't have josomycin to predict the model for the homology model? Well, I already have one set up, I believe. So if I go to temp, I should have, no I don't. Well, you know what, I think I can get it real quick, and then I can show y'all with the Swiss model using a different model, what the model might look like compared to the actual NMR predicted structure. So here's another homology model that I use. I use an alpha-like toxin to predict the structure of josomycin. I'm going to download this file. And I'm going to put this here. I'm going to rename it to alpha. And then from here, I'm going to open up PyMol, and I'm going to clear everything out of the way real quick, reinitialize everything, and then I'm going to fetch, and then I'm going to load alpha, and then I'm going to align these two now. So here we have our section here. Now you can see that with the homology model, it's lower. The root mean square deviation was lower compared to the quark and Scratch, but it's still not as good as Raptor. And in this case, we have decent root mean square deviation. It would be better if it was lower, but it makes sense because we used a protein structure that has a lower sequence identity. When we use a protein structure that had a higher sequence identity, 100%, we had a really, really low root mean square deviation, 0.35. So that's homology modeling, ab initio, the protein threading, for you and determining and comparing the structures. So some cases you might find that you might need to use one structure or the other, and this gives you an idea of sometimes the structures aren't going to predict exactly what it is. The structures aren't going to be 100%. You might get some deviation, and some of them are better than others in certain cases. Just depends on your situation.